Backtracking. By the end of this video, you will learn how to solve problems such as encoding problem, problems based on permutations of a set of numbers or symbols, problems based on finding all subsets or specific subsets of a set, and other interesting problems such as combination sum, word break, and traveling salesman. You will learn how you can tailor backtracking algorithm to solve all of these problems and many others in a very systematic way, and we will also talk about the coding details and implementation of all of them. Hello guys, I'm very excited to have one last video in 2020. Today we will talk about backtracking, which is a very common technique when it comes to interview questions. I will show you various examples with detailed implementation, and I will also show you several very common techniques that are used in solving backtracking problems. Also, I will show you how backtracking, DFS, recursive functions, and dynamic programming are all connected so that next time you see one of these problems, you don't feel scared, you actually feel like solving them is kind of fun. Please don't forget to subscribe to my channel, like this video, share it with your friends, and let's get started. Now, before we get to backtracking, let's get back to the basics and quickly review one familiar algorithm called Deferred Search. Deferred Search is a graph algorithm to iterate or search within the nodes of a graph. The algorithm is very simple. You start from an arbitrary vertex v, which we call it root, you mark that as visited, and then you recursively visit each neighbor of v that is not visited. For example, in this case, we have node 0 to be the root. We mark this as visited. Now I have to run the same algorithm on all the neighbors of node 0 recursively. First, we run it on node 1, so we mark this as visited. Now we have to run the algorithm recursively on node 1's neighbors that are not visited yet. The neighbors of node 1 are 0, 2, and 3. The only unvisited ones are nodes 2 and 3. So we run the algorithm recursively on these two. First, we pick node 2. Now I have to run the algorithm recursively on unvisited neighbors of node 2, which is in this case only node 3. So I move on to node 3, then I move on to neighbors of node 3, the ones that are not visited yet. And this way I will finish visiting all the nodes in the graph. Notice that we visit node 5 only after we visit nodes 1 and 2 and their children. And that's why we call this depth-first search, because you get to the nodes that are deeper earlier than the nodes that are close to your root. Let's see how DFS is implemented in practice. The input to your function is the root and also a data structure that specifies what node is visited. In this case, it's a map from integer, the node number, to a Boolean variable that specifies if that node is visited or not. First thing we do is to mark the root node to be visited, and then we iterate through all the neighbors of the root, and more specifically, only the ones that are not yet visited, and then we run DFS on them recursively. So we really iterate through all the unvisited neighbors, and then we run DFS on them recursively. And that's it. That's basically what DFS is in practice. How does DFS work in a tree? As you know, an important feature of a tree is that it does not have a cycle. Let's see how DFS works on an example tree. First, we visit the root, then we have to run DFS on all of its children recursively. First, we pick node A, we mark it as visited, then we run DFS on all the children recursively. In this case, we pick node D, and we keep continuing this algorithm. So we get to node H, then we get to node J. J doesn't have any children anymore, so now we recurse or return, and we move on to the next child of node H. In this case, we visit node K, then we recurse back to node D, and then we visit node I. There is no more children, so we go back to node D, back to node A, and we visit node E. And we keep doing this until we finish visiting all the nodes in the tree. As you noticed, we visited these nodes that are deeper earlier than these nodes that are closer to node root, hence the name depth first. Let's get back to implementation. As you remember, this was the implementation of DFS in a general graph. And remember that we used this visited because we didn't want to visit a node twice. And this only happens when you have cycles in a graph. For a tree, you don't have a cycle, therefore you don't need this visited data structure anymore. So we can tailor this to tree to something like this, which only has the root as the input. It's enough just to iterate through all of its neighbors or all of its children and run DFS on them recursively. So you can see that DFS is much simpler, has a much simpler implementation in a tree. Now let's see how DFS works in binary trees. In a binary tree, each node has only two children, the left child and the right child. Therefore, you don't need a for loop. You can just directly call DFS recursively on each child separately. Also, if you use pointers, you need to check to see if the given node is null. In this case, we have to return, which indicates we just came from a leaf. You guys are probably familiar with the Fibonacci function where f of n is equal to f of n minus 1 plus f of n minus 2. And your base case is when n is equal to 0 or n equal to 1, which you return 1. Now, if you look at the structure of this function, you will see that this is really running DFS on a binary tree. This is the left child, this is the right child. And then at the end, we sum up the return values of the left child and the right child. Now, I talk about this because this implementation of Fibonacci function is a great example of the case that we are running DFS without having the graph stored in the memory. Basically, there is no graph stored in the memory. We kind of create it as we call the functions recursively. We calculate each node's value and we move on without storing that value in the memory. So what you need to take away is that for running DFS, you don't necessarily need to have the graph stored in the memory. You can build it as you go. With this introduction, now let's get to backtracking. The good news is that because you know DFS, you already know backtracking as well. Backtracking is a technique based on DFS. So you can say backtracking is really DFS plus or minus some extra work. We will talk about what this extra work is in a minute. And when you're running backtracking technique, the graph that you're running DFS on is often created on the fly. So that the graph doesn't exist in the memory. You create the graph as you run your DFS algorithm at the same time. Let's look at an example. This is a famous example, Leetcode problem number 46, that asks you to find all permutations of a given set of distinct integers. For example, if your input is a vector of 1, 2, and 3, your output should be a vector of vectors where each element is one valid permutation of the given input. How should we solve this? The way to approach problems like this is to create the search space tree. If you want to iterate all permutations of 1, 2, and 3, you need to go step by step. At step 1, we have 3 options to pick one of these elements. It has to be either 1 or 2 or 3. Now at step 2, when you pick element 1, the step 2 is either picking element 2 or picking element 3. Now that you pick element 2, your final option is to pick element 3. If you pick element 3, your final option would be picking element 2. Similarly, we can iterate all other options and create them one by one and create this tree. Now, the permutation that you want is the path from the start node to a leaf node. For example, in this case, the permutation is 1, 2, 3. In this case, is 1, 3, 2. The other one is 2, 1, 3, 2, 3, 1, 3, 1, 2, and 3, 2, 1. So if you can see that if we had this graph in the memory, all you needed to do was iterate this graph using DFS, and then whenever you get to the leaf, you just print out the current path. Now in practice, rather than storing a graph like this, which in general might be huge, we basically create these nodes as we run the DFS at the same time. I will show you this in a minute. Now let's look at the implementation of a function that generates this tree on the fly and runs DFS on it at the same time. This function, we call it permute auxiliary. It has one parameter, which is basically your input. So this is given. We also have 2 auxiliary parameters. One is result, which basically stores the leaf values, stores the current path at the leaf, in this case 1, 2, 3, 1, 3, 2. So as we get to the leaves, we push them inside the result. And there's another parameter that we use, current result, which basically holds the current path. For example, in this case, when we are at node 2, the current result should be 1, 2. When we are at node 3, the current result should be 1, 3. When we are at node 3, the current result should be 1, 2, 3, and so forth. Having defined this function, our top-level function, which only has one parameter, the given input, looks like this, which basically constructs this result vector of vectors and calls this permute args with the given parameters. So the result we just constructed, and the current result, because at this node, the current result is empty, we just pass an empty vector. At the end, we return the result as our output. Next, let's look at the implementation of permute auxiliary. First, we need to check if we are at a leaf. If we are at the leaf, we should store the current result inside the result and return or recurse or backtrack. Now, if you're not in a leaf, just like DFS, we have to iterate through all the children of each node. So this is nothing but our familiar DFS loop to iterate the children. The children, all the options that you have for each node, are chosen from your given node, except that we have to omit the ones that show up on the current path. So for example, here under node 1, our options are only node 2 and 3, but not node 1 because 1 showed up here already. under node 3, our option is only node 3, not node 1 and 2, because 1 and 2 already exist in our current path. So all we are doing here is just avoiding duplicates. Now, once we do this, then we have to call DFS, or this permute auxiliary function, on each child recursively, separately. In order to call this function, we have to adjust the parameters correctly. In this case, the result is okay. Nums is the same nums that was passed to us, so it doesn't change. The only thing that needs to be updated is the current result. So as we go to the next child, we have to concatenate the next child to this vector. So I concatenate 2 to 1, and I get 1, 2. And that's what we're doing here. We basically get the current result, concatenate or push back the child that we are adding, and then we pass it to permute aux. And that's it. Notice that there's no graph really existing in the memory. We don't store the graph. We kind of visit each node on the fly without storing it. But notice that everything else is like our familiar DFS implementation. There is a check for the leaf because we have to gather and store the results at the leaf. And then there's a for loop that iterates through all the children. You have to be careful to generate the children correctly, basically take out the ones that are valid based on the current result. And then also, the other thing that we need to do as extra work is to adjust the parameters correctly when you call the next function recursively. This slide shows how current result parameter changes as we call DFS on each node separately. First, it's empty. Then for node 1, we concatenate 1 to empty, it becomes 1. Then we concatenate 2 to this vector, it becomes 1 and 2. At the end, we concatenate 3 to this vector, it becomes 1, 2, 3. And because this is a leaf, this is one of our answers, and we store it. Now, we are not doing everything optimally. At this part of the algorithm, we keep copying one vector to another, and then we add something to the end of it. And since you're doing this in a loop, the runtime can be non-negligible. So what if we avoid this by not copying it, but just using the current result as is, modify that and adjust current result, and then pass it to the permute aux? Basically, what I'm saying is that if your current result is this vector here, which has one element, what if for each child, we add that child to the vector that is given to us without copying a new one? So we just add 2 at the end of it, and then we pass to the recursive function. So now when we are backtracking from this branch and go to this branch, we have to revert this vector to what it was, and then add this child to the end of it. So we originally had 1, we add 2 to the end of it, and then we went down this branch. Now we come back, we convert this back to what it was, and then we add 3 to the end of it, and then we go down this branch. This can be translated to code by taking current result, add nums I to the end of it, call our recursive DFS call, and then use popback to remove this for the next child in the for loop. Also, notice that current result doesn't need to be passed by value. It can be passed by reference. So we save 1 copy here. We save 1 copy here as well. So this is the same algorithm, just a little bit more optimized, avoiding extra copies. Now, before I move on, let's see if we can generalize this to a generic solution for backtracking problems. So please remember exactly what we did. We created an auxiliary function with a given parameter and 2 extra auxiliary parameters. One is gathering all the results, the other one gathers or stores the current result up to that node. For this problem, whenever we detected a leaf, we simply store it in the result and then we return. In some other problems, you may want to find the minimum among all leaves or a maximum among all leaves, or you want to add them all and find the sum or the total, or you want to count how many leaves have a certain property. So based on what your goal is, you do something at this point. Next step was to iterate all the children and then run DFS on each child separately. Now, as you are iterating through all the given input values, you might realize that some of them are not appropriate, so you have to find a way to filter them out. So this is another next important step that we took, was avoiding invalid children. So basically you filter out the ones that are not valid children. After that point, everything is easy. You just have to adjust your auxiliary parameters for your next DFS call, which is one of the children. And then once you are recursing or returning from this call, you have to reset the auxiliary variables to what they were before, which is what we are doing at this step. Okay. So to recap, most backtracking problems are more or less solved like this. You have a function like this with some auxiliary parameters. You check for the leaf, you iterate through all the children, you filter out the ones that are not valid, you update or adjust your auxiliary parameters, you call your DFS function recursively, and then you reset your auxiliary parameters for the next child. Let's look at a more complicated example. This is Leetcode problem number 47. Find all permutations of a given list of digits which may have duplicates. For example, in this case, the value 1 is duplicated. You have 1, 1, 3. You want to find all the valid permutations of 1, 1, and 3, which is this. This has to be your output. Now, again, just like any backtracking problem, you should start creating the search tree. In the beginning, your options are either 1 or 3. Notice that we have duplicated ones. There's no way to distinguish between them. So basically, you only create one node for your duplicated ones, not two of them. Same thing here. If I choose node 3, then my next option would be 1. I don't put another node 1 here because I can't distinguish between these two cases. The current result here is empty. For this node, it would be 1. For this node, if I did choose to create another node by value 1, the current value would have been also 1, and there's no way to distinguish between these two cases. Same thing here, when I created node 3 and then I chose node 1, if I chose another node, the other node 1 here, then the current result for both of them would have been 3 and 1, and there's no way to distinguish them. So that's why at each horizontal level, we only have one of each duplicated values. However, as I go down, I can select the other one, and the current value becomes 1 and 1. And then after that, I can pick value 3, and then the current value would be 1, 1, and 3. So again, our leaves will show the valid permutations. 1, 1, 3, 1, 3, 1, 3, 1, 1. So all you need is an algorithm that generates this tree on the fly and also runs DFS on it at the same time. Remember that previously we had a vector called current result, which would store the current path coming into each node. And it was empty in the beginning. As you add each node, you add it to the end of the vector. So here I'm adding 1 to the end, here I'm adding the next one to the end, and here I'm adding 3 to the end of this vector. Previously, when we were generating the children for each node, we used find function inside current result so that we prevent the same number to be added under its parent. And that worked because previously we didn't have any duplicates. Now that we have duplicate, this method doesn't work anymore because as I'm adding this one, there is already a 1 in current result, and that prevents me from adding the second one. In order to address this, instead of using find, we use another auxiliary data structure, namely a vector of booleans, which has a corresponding element for each item here, which basically tells us if it has been used or not in the current result. And we only accept the children that are not used yet. So used is first initialized to all false. When I add the first item, I set the first item in use to be true. When I add the second item, I set the second element to be true. And then when I add the third item, I make the third item in the used vector to be true. The next thing that we should handle is to deal with duplicates in one level. As we talked before, you don't want to have nodes in the same level with the same value. Although these are two different items, because their value are the same, they are duplicated, we don't want this situation. So this second if statement deals with that case. Basically, first we sort all the inputs so that the duplicates are next to each other. And then once we detect the current item is a duplicate, basically it is equal to its previous item, and the previous item is being added as a node, the previous item or one of the previous items is being added as a node, we don't want to add the next item. So this if statement takes care of that case. With these two simple modifications, everything else is very similar to our previous example. This shows the complete algorithm. The inputs is given a vector of integers, and then we define 3 auxiliary parameters. Result and current result are like before, and then used is the new vector that we just talked about. Just like before, we first checked for leaves. If it was a leaf, then we push current result into result and then we return. Otherwise, we have to run DFS on children. As we iterate through nums, we have to avoid duplicates. These two if statements avoid having duplicates. The first one is to avoid duplicates going down, and then the second one avoids duplicate horizontally, just like what we talked about. And the last 2 steps are very straightforward. First, we adjust our auxiliary parameters for the next recursive call so that they look like what they were as we enter the function for the next child. So with that definition of the auxiliary function, our top level function or main function that has the input nums is responsible to construct result, used, and current result, sort the input, and then call the auxiliary function using these parameters, and then return the result. Up next, a very famous problem called traveling salesperson or traveling salesman. In this problem, we're given a list of cities and the distances between each pair of cities, and we want to find the cost of the shortest possible route that covers each city exactly once. And for simplicity, we assume the problem also tells us what city to start from, so we have to start from the given city and then cover each city exactly once, and then go back to that starting city. The graph information is given in the form of a two-dimensional matrix, where each element at position I and j corresponds to the distance between city I and j. And the output of our problem is the shortest distance. The brute force solution of this problem is very similar to the permutation problem that we saw before. Basically, we try all different combinations and then we find the minimum cost among them. So if the problem asks us to start from node 0, then our next option would be either node 1 or 2 or 3. Once you pick node 1, your next option is node 2 or 3. Once you pick node 2, your next option is 3, and then you have to go back to node 0. We introduce two auxiliary variables, one called current path, which is similar to the current result that we saw before. It's a vector that holds the value of all the nodes that we have seen so far. And the other is the current cost, which holds the cost of the path so far. So when we start, the cost of the path is 0, and the current path is a vector that has only element 0. As we go down and do our DFS, we update these two variables. For example, when we go from 0 to 1, we add 1 to the end of this vector, and we update the current cost with the previous cost plus the weight or the cost of going from 0 to 1, which is 40. Now, when we go from 1 to 2, we add 2 to the end of this vector, and then we add the cost of going 1 to 2, which is 30, to the previous value to get 70. When we go from 2 to 3, we add 3 to the end of this vector, and then we add the cost of going from 2 to 3, which is 30, to our previous cost to get 100. And then finally, we go to node 0, so the total cost is 135. So if you complete this for our various permutations, you end up with these leaf variables, and then finally you have to find the minimum among them. In this case, we have two answers, going from 0 to 2 to 1 to 3 back to 0, or going from 0 to 3 then to 1, then to 2, then go back to 0. Our top-level function has two parameters, the start node and a two-dimensional vector representing the cost of traveling between each two cities. Our auxiliary function has some extra parameters, current node, the node that we are working on, current cost, the cost of coming to that node, and current path, the path from start to that node, and then two other parameters that keep track of minimum cost and minimum path at the leaves. First thing we do is that we need to check to see if we are at the leaf. If that's the case, we update minimum cost and minimum path. Otherwise, we go through all the nodes, and then just like the permutation example, we filter out the ones that are currently seen or exist inside current path. Then we update current path. We call our recursive function with current path, the updated value, and also the updated value of current cost, which is current cost plus weights of current node to node I. And then finally, we reset our current path. We can make this algorithm slightly more efficient. Suppose this is our search graph, and somewhere down here at the leaf, we find that our current cost is 95, and then we update our minimum cost to be 95. And then suppose here our minimum cost is still 95, and we found that our current cost is 100. So at this point, we know that there's really no point to go down because the value of current cost is only going to get worse. And because we know that there's a better answer here, there's no point in evaluating this node and all of its children and grandchildren. And that's why as soon as something like this happens, we can immediately return or backtrack and continue the rest of the algorithm. This is still DFS, except that we kind of skipped evaluating part of the graph because we already know there's nothing there for us. This is where the backtracking algorithm got its name, which is as soon as we see a node doesn't give us the correct answer, we kill that node, we don't evaluate all of its children and grandchildren, we backtrack and continue searching in other branches. Enhancing our previous code to have early backtracking is very simple. We just add one line here, one if statement, to compare current cost against minimum cost. If that's the case, we return immediately. This way, we were able to skip this for and all of these recursive calls associated with this for loop, which might be very significant in practice. Up next, backtracking meets memoization or dynamic programming. We previously saw the Fibonacci function can be solved using DFS by recursively calculating f of n based off f of n minus 2 and f of n minus 1, where your base cases are f of 0 is equal to f of 1 is equal to 1. For example, when you calculate f of 5, you have to calculate f of 3 and f of 4. When you calculate f of 3, you have to calculate f of 1 and f of 2. When you calculate f of 2, you have to calculate it based on f of 1 and f of 0. Now, when you calculate f of 4, you have to calculate f of 2 and f of 3. But when you do this, you realize that you already have calculated f of 2 before, and you already have calculated f of 3 before. This concept is called overlapping subproblems, which basically means if you already solved a subproblem to your main problem, do not recalculate it again. Or in other words, if you already evaluated a node, do not re-evaluate that node in the tree over and over again. Just memoize its value somewhere, and then whenever you need to calculate it again, just quickly look it up and do not expand these nodes. This can significantly increase the runtime of your algorithm. And this is what is called memoization. If you need to know more details about what memoization and dynamic programming are, you're welcome to watch my video on dynamic programming. But for now, I think this is enough introduction to be able to solve a more complicated backtracking example that requires memoization or dynamic programming. Let's look at this example. This is Leetcode problem 140. We are given a string that doesn't have any spaces. Your goal is to break down this string based on the words inside this dictionary. Basically, we need to insert spaces inside this string so that the resulting string, all the words inside the resulting string are words from the dictionary. So for this example, we can see there are two answers. You can either go with cats and dog, or you can go with cat, sand, dog, which are all words inside this dictionary. So our goal is to find out how many times you can do this. The solution to this problem is very simple. Basically, each time we can look at the string and find out what are the words that can match to the beginning of this string. For example, in this case, there are two words that I can match to the beginning of the string. It's either cat or cats. And these are the options. These are the nodes inside our DFS tree. So you start with this string. You can either go with cat or cats. And then what remains is sand, dog. In this case, what remains is and dog. Each time we find a match inside the dictionary, we add it to the current result and we go down the tree. So after this sand, dog, there's only one word that matches the beginning of the string, which is sand, and what remains would be dog. So we add sand to the dictionary, we go down one more level, and then the last word in the dictionary would be dog that matches this dog. After that, what remains is an empty string, and then we add this to the result, and then we realize that because this is an empty string, we are at a leaf, so this has to be added in our final result. So cat, sand, dog. And then you can go through this path and get to cats and dogs. So this is our very familiar and simple backtracking algorithm or DFS algorithm that evaluates all the nodes and then at the leaves stores the result. Let's code this up. We create an auxiliary function. These two are our given parameters, s and the dictionary, and then we have two auxiliary variables, current result and result. If we are at a leaf, that means if the size of the string is 0, if this is an empty string, all we have to do is to convert current result by joining all the strings inside this vector and create a string, which then we push in our final result and then we return. If this node is not a leaf, then we have to go through our familiar DFS loop to evaluate all the children. So we go through all the words inside the dictionary to find out which one of these words matches the beginning of this string. So this function, basically all it does is it's checking to see if the word inside the dictionary matches the beginning of the string. If that's the case, then we find a valid child. So then we have to adjust s, we create new s, which basically has the rest of the string. This is what we're doing here using substr. And then we add word to our current result. We call our recursive function, and then we reset current result back to what it was so that it works for the next child. And that's it. That's all it is to this algorithm. It's a valid solution and it should work. Our top level function, which only takes the string s and the dictionary, is responsible for constructing result and current result, passing them to the auxiliary function and then return the result. So this solution works, except that it takes a really long time to finish. In fact, if you submit this on Leetcode, you would see that you get an error, time limit exceeded. And this is the example on which our current solution takes a really long time, which is not acceptable. So that means we have to be a little bit smarter and make our algorithm more efficient. And that's where dynamic programming or memoization come in. Let's look at this small example. If your string is A, and your dictionary is either single A, double A, triple A, and 4 A's, then our tree would be something like this. So we can either break this using A, or break it using double A, or triple A, or 4 A's, which are the children of the root of this tree. If we break it using only 1A, what remains is triple A. Next, we can break this string either using 1A, double A, or 3 A's. So you can complete this tree and come up with the leaves. Everything is fine, our algorithm works. However, if you really pay attention, you would see that there are cases that we are re-evaluating the same thing over and over. So here, when our current string is AA, we are basically adding the same postfixes to our current result, which is A space A or double A. We are doing the same thing here. Our current result is AA. And we're adding the same postfixes, A space A or double A. So this means that if we were smart, we could have prevented this recalculation. And then as soon as we knew we have calculated this again, we could have just concatenated these postfixes to our current result right here without going down the tree and calculate the result more efficiently. So this suggests that we need to create a memo, which is a map of strings, which is our given string, to the postfixes that we add at the leaves. So it would be a map of string to a vector of strings. We make a couple of changes to our auxiliary function. First, we add the memo as yet another auxiliary parameter. Secondly, the return type of our auxiliary function is now a vector of string. This type matches the values inside the map. So basically, our function returns for each string the postfixes that should be added to the current result. This return value either exists in the map, or if it's not in the map, we have to create it. Just like any other memoization algorithm, we first check the memo to see if there's an entry for the given string. If that's the case, then we have to take the current result, in this case, for example, AA, and add all the values in the map to the current result and push them inside the final result. And that's what we're doing right here. Again, this join function, I'm not showing its detail, but what it does is that it converts a vector of string to one string and adds spaces between each string. Next, there's a special case where the given value s is of size 0 and if it's empty. If that's the case, that means we are already at a leaf. So all you need to do is to convert the current result to a string and push that string directly inside your final result. And your return value, because our input was an empty string, is just a vector of empty string. And finally, if the value was not in the map, then we have to actually evaluate each child separately. So that is our for loop, the familiar DFS loop. And this is what we had before to check and see if each word inside the dictionary matches the beginning of S. If that's the case, then we adjust S and current result. We call our recursive function. And remember that what returns from our function are these postfixes. So what we need to do is to create this map is to take each of these values and add the word from the dictionary, concat the word from the dictionary to what is returned to get the entry for that node. And that's what we are doing here. And then finally, we reset our current result for the next child. At the end, we return memo of S. So memo of S is getting its results from all the children, and then finally we return the value. This shows the complete code that we just talked about. The first part, we first check the memo. The second part is checking to see if the string is empty. And then finally, we evaluate all the children and run our familiar DFS loop where we call our auxiliary function recursively. So there you have it, guys. This is a more efficient implementation of the same algorithm. It's still backtracking. However, we made it more efficient. And in many cases, when you already have a memo calculated, you are avoiding going through this loop and you're avoiding calling a lot of recursive functions because you already have the result in your memo. Up next, example 5. Let's talk about this very famous example. Maybe I should have talked about it in the beginning of this video because this is the classic example where everyone talks about when they want to teach backtracking. And the problem is that we have a chessboard which is of size n by n, and your goal is to place n queens inside this board such that no two queens can attack each other. If you remember from chess, queens can attack all the pieces in the same column, or all the pieces in the same row, or all the pieces diagonally. So our goal is to find a combination of these n given so that no two queens can attack each other. The intuition of solving this problem is very simple and straightforward. So we know that each column can accept only one queen, because as soon as I put one queen in this column, no other queen can be placed here because that one queen will attack. So that suggests that we have to put one coin in this column, then put one coin in this column, then to column 2, then to column 3. So there's no option or choice here. We have to go column by column and step by step. However, at each column, you have multiple options. So when j is equal to 0, you can either put the queen in column 0, or you can put it in column 1, or you can put it in column 2, or you can put it in column 3. So for each column, you have multiple options. And then you move on to the next column. Again, you have multiple options for the row. This shows part of our DFS tree. So first, I'm at column 0, and I have options to put at I0, 1, 2, or 3. Let's say I put the queen in J0 and I0. Next, I go to J is equal to 1, and again, I evaluate to see which row I should consider, either row 0, 1, 2, or 3. However, notice that row 0 wouldn't work because this queen can attack, so we have to return or backtrack. Row 1 also doesn't work because the queen can attack diagonally, so again, we have to backtrack. And then row 2 would work because these two queens cannot attack each other. So this is a valid node. These two other nodes don't work, so we have to kill them. And again, this is where the name of backtracking has come from, because you evaluate a node, and if you see that node doesn't work, there's no reason to move on and generate the nodes under this one. And we basically say backtrack to evaluate other options. To represent the board, we use a two-dimensional vector or two-dimensional array of integers, where a 0 means there's no queen at that location, and a 1 means there's a queen at that location. Our auxiliary function has one auxiliary variable, which is solutions. It's a vector of boards, which is a vector of all the valid combinations of queens. Next, you have the board itself, and then we have our current column, j, and then finally you have n, the value of n, which you could also get from the board size, but we can have it here as a convenience. So now, if j is equal to n, that means we are at the last column, so that means we are at the leaf, so all you need to do is to push that board, that combination to our final solutions and return. Otherwise, you guessed it right, we run our familiar DFS loop for all the children, and our children are all the rows. Of all the rows, we have to pick the one that is valid. So we have a Boolean function, I will talk about the details of this later, which basically returns true or false if putting a queen at that location, I and j, is valid or not, if the queen at I and j would be attacked by other queens on the board. So this simple function checks for that. If the queen at location I and j is not being attacked by current queens in the board, it returns true. So now we can put a queen at location I and j, which just means set that value to 1. Then we call our function recursively, and then we go to the next column. Once we come back, we have to reset our board for the next child. Let's talk about the details of can place queen. As I mentioned, it takes a board and the row and the column. So we want to evaluate and see if we can place this queen, a new queen, at location I and j. All you need to do is to check and see if there's any queen already to the left of this queen in the same row, or if there's any other queen to the up left diagonal of this queen, or if there's any other queen already to the left bottom diagonal of this queen. And that's why we have 3 for loops. We check for these 3 cases. If any of these conditions hold, we return false, otherwise we return true. Turns out when n is equal to 4, there's only 2 solutions, which I'm showing here. It's either this combination or this combination. Up next, I want to talk about 2 more examples which are related and I think are very interesting. So the first one is that you are given a set of numbers. So this is really a set. And what you need to do is to create the power set of the given set. So basically, we have to create all these subsets of the given set. So in order to solve this, again, let's create the DFS tree. So in order to produce a subset for each item, we have to decide if this item exists or does not exist. So we create x0 representing if 0 in each of these subsets exists or not, and then x1 represents if 1 exists or not, and then x2 represents if 2 exists or not. In the beginning, we have 2 options, x0 being 0 or x0 being 1. If x0 is 0, then for 1, we have 2 options. It's either x1 being 0 or x1 being 1. Once we pick x1's value, then we have 2 options for x2, either 0 or 1. And once you get to the leaf, so for example here, At this leaf, we have x0 and x1 and x2 all being 0. That means none of them exist in the result, so this should be just an empty set. Here, 0, x0 and x1 are 0, but x2 is 1, so we only have 2. Here, there's only x1 is equal to 1, so we only have 1. Here, we have x1 and x2 being 1, so we have 1 and 2. And we can continue creating all the leaves. And whenever we get to the leaf, we add the leaf to our final result. So that means we can code this up using this very simple code here. Our auxiliary function has one auxiliary variable called result and current result and the index, meaning what x index we are deciding about right now. If index is equal to num's size, the size of the array, that means we are at the leaf, so we should push the current result inside the result. Otherwise, we have to go and generate all the children. Next, we should generate the children. We only have two cases where either x index exists or it doesn't exist. If it doesn't exist, we pass current result as is. We only add 1 to the index of x index for the next child. If it does exist, we add it to the current result. We call our function recursively, and then we reset our current result. And that's it. That should work and generate all the subsets for us. This problem can be solved in a different way, still backtracking, and I think it's interesting to see that other solution as well. So we are still doing the same thing. We're given with a set of numbers, and we want to create all the power sets. Now our tree can be considered in a different way. So I can say, in order to generate these subsets, I can either add element 0, element 1, or element 2, or do not add element and consider this a subset itself. So this would be one of my leaves. Now for these other nodes, let's talk about this one, for example. When I pick 0, I can declare this itself to be a subset, so this would be a leaf itself, or I can add 1, or I can add 2 to it. Let's say I add 1, so then I can consider that 0 and 1 itself to be a subset and a leaf itself, or I can also add 2 to it, and then I can declare this as a leaf, so that would be 0, 1, and 2. And this way you can generate all the subsets in a different way, still backtracking, just a different kind of tree. Let's code this up really quick. Now our auxiliary function has the auxiliary variable result, auxiliary variable current result, and we also have an index, meaning what item we are adding. So as we go down the tree, the index is incremented 1 by 1. So the interesting part is that as soon as we come for any input, as soon as we enter this function, we can declare current result as a leaf itself. So there's no if condition here. We directly add current result to our result. And then we generate the branches. So we go through all the items in the input set and we add them to our current result. We call our function recursively, we increment the index, and then we reset our current result for the next child. And that's it. This is also another valid solution, still backtracking for the same problem. One last example. This is a very similar problem, Leetcode number 90. We're still generating the power set, except that in this case, the values in the given set, or in this case, I should call it a vector or a multi-set, the values can be duplicated. So our task is to generate all the possible subsets. So in this case, for example, for 1, 2, 2, we get 2 or 1 or 1, 2, 2, 2, 2, because 2 is duplicated, and then we have 1, 2, and then the empty set. Using the second solution of the previous example, we can simply draw our tree to be like this. Similar to one of our previous examples, the way we deal with these duplicates is that we prevent having duplicate options in each level. So in this case, for example, I can either pick 1 or pick 2. I cannot pick 2 nodes with a value of 2. But the rest is similar to the previous example. So I can either select 1 or select 2 or select nothing and declare this as a solution and as a leaf. If I pick 1, I can either declare that itself to be a leaf, or I can add 2 to it. And then if I do this, I can declare that itself to be a leaf, or I can add the next 2 to it and then declare that as a leaf. So this way I can generate all the leaves, and that would be my solution. Let's quickly code this up. So again, I have my auxiliary function. It has the auxiliary variable. It has the auxiliary parameter result, current result, and index. Each time we enter this function, the current result by itself is pushed back into a result. It's a leaf by itself, but we can also generate the branches. So we iterate all the items in the given set from index to the end. We skip the duplicates. Remember that we need to skip the duplicates in each level. So that's how we do it, by comparing nums I is equal to nums I minus 1. If that's the case, we skip that child. Otherwise, the rest is like before. And we can only do this if nums is sorted. So remember that our top level function before calling this auxiliary function has to sort nums just like before. We update our current result, call our function recursively, add to the index, and reset our current result. Before we finish, let's quickly summarize what we learned. So we saw that backtracking is almost DFS. It's basically backtracking is DFS plus or minus some work. First of all, the DFS graph is usually created on the fly. The graph is not given to you. You have to create it on the fly and run DFS on it as you go. Now, there are various techniques to enhance and speed up this DFS algorithm. One would be early backtracking, hence the name of the backtracking algorithm. As soon as you find out one node is not going to result any answers, you kill that node and backtrack to the next ones. And then we also saw that dynamic programming or memoization can prevent recalculating the same result. So basically, if you see you already evaluated a node and that node repeats itself in your tree, you memoize its result and then you use it later. Let's quickly review all the common techniques that we learned to solve backtracking problems. The first thing that we learned was to use this current result and carry current result all through the graph. So basically, we created an auxiliary variable, and then we update it at each time that we're visiting a node. And then once we get to a leaf, we basically push current result inside the result. This is a very common technique in backtracking algorithms. Next, we learn how to reject invalid children. Basically, as you are writing your for loop and you're going through all the candidates for generating the children, you often need to filter some of them out. In one case, we saw that you have to search the current result. This was in the case of permutation. In another case, where we had duplicates, we saw that current result search wouldn't work, so we use another vector that marks the ones that are used, so we avoid them. The other technique for this filtering was to use an index. So in the subsets example, we saw that rather than searching from index 0 in the nums vector, we use an index, and then each time we increment the index so that the ones that are used, the elements in nums that are used before, are not used in the next children as we go down the tree. And finally, we learned this cool technique on how to deal with duplicates. So as you're going through your candidates for the children and you have duplicates, you often don't want to generate duplicate nodes or nodes with the same values in the same level. Instead, you want to put them as you go down the tree. In order to do that, we often sort nums. So you have to sort this in the beginning, and then you can compare nums I and nums I minus 1, so that if these two are equal, that means they are duplicated, and then you can skip them and avoid having duplicates in the same level. And I hope you saw that backtracking, recursive functions, and dynamic programming, and DFS for that matter, they're not scary things. They're all very similar and close concepts. So they're all really the same thing, which is creating a DFS tree and evaluate all the answers, except that dynamic programming and early backtracking are helping us to do this more efficiently. So in my opinion, you should make sure that you learn all of them together and don't be scared of them as very scary techniques or algorithms. Once you have this vision that they're all related, then you just have to learn one thing, and that would be super easy, hopefully with a lot of practice and solving a lot of examples. That's it, guys. Thank you very much for watching this video. I wish you the best in your exams and your job interviews. Please let me know if you have any questions in the comments. Also, please go ahead and like this video and subscribe to my channel, and I hope to see you guys in the next video. Thank you.